So when you talk about this Gibbs free energy, and just like before, if you see delta G naught, okay, which is your change in Gibbs free energy, if you see a naught, that zero up there, that just means it's under standard conditions. 1 molar, 25 degrees Celsius, standard conditions. So one of the things that you can look at, just like if you look at E naught can tell you whether or not a reaction is spontaneous. So if you start with this idea of E naught, what has to be the sign of E naught to indicate that you have a spontaneous reaction, positive or negative?
Positive.
Okay, so a positive E naught is going to indicate that you have a spontaneous reaction. So E naught standard comes from your standard reduction potential. That's old school. That's why you learn reduction potentials before you learn Gibbs free energy. This F is called Faraday's constant, okay? So if you look at what this number is, there's a couple of different ways that you can express the units on this. One's kind of more functional. But the basic idea is that Faraday's constant is the total amount of charge on 1 mole of just electrons. Okay, so that's why it's coulombs per mole. Because if you take the amount of charge on a single electron, which is 1.60 times 10 to the negative 19, and you multiply that by Avogadro's number, 6.02 times 10 to the 23rd, depending on how you round it, you're basically going to get 96,500. Okay? So that's why it has this specific value. So the pure application of this says, oh, that's coulombs per mole, because that's the amount of charge that exists per mole of electrons. So the important part of this is that this is per mole. If you look at your E naught values, like for copper, you know, that's just like 0.34 volts, whatever that is. Here's going to be the subtlety. If you look at your E naught values, there are no per mole considerations. It's just 0.34 volts. This is why we never worried about the mass of the copper strip, or the size of the copper strip, or the density of the copper strip, because it didn't matter. All you had to have was some copper, because this value is what's known as an intrinsic property. As long as you just have copper, that's going to be your reduction potential. As long as you have some zinc, that's going to be your reduction potential. The amount of copper that you have doesn't matter, because it's just a number. Now, when you get Faraday's constant, because that's coulombs per mole, obviously if you have 2 moles of electrons, you're going to have a lot more charge than if you just have 1 mole of electron. So this is going to be important. You need to realize, when is the concept of the mole important and when isn't it? So your E naught values don't matter. It's just a number. Hey, 0.34. The amount of energy, or the amount of charge that you have, is dependent upon. Because now this is going to be coulombs per mole. In terms of units, where this is going to play out, if you look at this negative N, and then Faraday's constant, and then you're multiplying that by your E naught value. So this is where this becomes important. So your N is going to be the number of moles. So this is the same N that we did when we used the Nernst equation, or the Nernst equation as Kevin calls it, okay? So that N has to, listen to me, has to come from the overall balanced reaction between, then this is always going to happen with the redox reaction, okay? Because something has to be reduced, something has to be oxidized. So this is going to be that least common multiple in terms of the number of electrons. So if you have 5 and 2, oh hey, that value is going to be 10. This is why you have to balance the half reactions, because you have to know what the value of N is. You just can't randomly, oh, I'll just pick one. No, okay? It has to come from the balanced reaction. So technically, when you look at this Gibbs free energy value, so we'll talk about why that negative sign is out there in just a second. So N is going to be the number of electrons. And then you have Faraday's constant, which is joules per volt mole. And then you have your E naught value, which is in volts. Okay? So what's going to happen then is that your volts are going to cancel out. And then what you're left with is joules per mole. So what that tells me is that the amount of Gibbs free energy that's available is dependent upon the quantities that I have because of the fact that this is joules per mole. So what you're going to see is that when you get into thermodynamics, which is going to be the next big unit, is that what?
Nothing. It's just when in Chem 2, the thermodynamics section on the final was my worst section by a lot.
Okay. Well, that's
I
optimistic.
just yeah.
Okay. Now, here's the thing with Gibbs free energy in terms of sign. So, if you're going to have a spontaneous reaction, you have to have a negative delta G value. Okay? And this is going to be true no matter how you calculate Gibbs free energy. And we're like I said, we're going to end up with 4 different ways to calculate Gibbs free energy. If it's a spontaneous reaction, no matter how you calculate it, it's going to be negative delta G. So this is why this negative sign lurks out here. So if you have a spontaneous reaction, that means that you're going to have a positive E naught value. Cool. Faraday's constant, that's just a number. That can't be negative. Your N is the number of electrons from the balanced equation. That, you can't do anything with that. That's a positive value. So the reason that that negative sign lurks out there is to make the signs work out. Because if you have a positive E naught value, that means that then you put that negative sign on it, then you get a negative delta G. Oh, hey, the reaction becomes spontaneous. If you have a negative delta E naught, indicating that it's not spontaneous, then you have a negative delta E multiplied by another negative, and then you get a positive value, and then you get a positive delta G, which indicates that it's not spontaneous. Okay? So that's why that you think, so why is there a random negative sign out there? That's why, so that it fits in the overall scheme of things. Now, what if your E naught value is 0? You're not making this difficult.
It's 0.
It's 0. Guess what? You're not going to have any free energy because of the fact that there's no voltage. Okay? The electrons are not going to move. You don't have anything available to you. You don't have any free energy available to this. Okay? Now, when you look at, sometimes this plays out differently. So, sometimes you're going to see this written as work max. So for those of you that haven't studied physics yet, when you look at work from a physics perspective is multiply 2 things together. It's force and distance. And it goes back to the same idea, is that if you don't have any energy, you can't do any work. You can't exert a force through a distance. So Saturday morning, Cohen's mom knocks on the bedroom door and goes, "Hey, we got company. You need to go feed the chickens." Okay? Right? And Cohen says, "Oh my God, Mother, I don't have any energy. I have no free energy or any form of energy." So what he is saying from a physics perspective is that he is incapable of exerting a force over a distance. I cannot lift up the can of chicken feed and pour it. I cannot do work. I cannot exert a force over a distance. I think that might be a valid story.
Yeah, except she wouldn't knock on my door. She would just get mad at me later.
Well, okay, fine. whatever. But the point being, your argument is that you have no energy. I cannot exert a force over distance. So if you see work max that can be done by a cell, all it's asking you is for the amount of Gibbs free energy. Okay, don't flip out and go, oh my God, no, don't worry about it. Okay, so here's how this plays out. Simple example. Hold on, I just had. Hold on. Today my organization skills are
Today.
I thought I grabbed the right one. I didn't. Yeah, don't flip out. Don't,
I don't know, Bert. We're getting a little iffy right now.
don't, I got faith. Don't flip
Is
out.
that-
Silver
or is
and
that
oxygen
hydrogen
plus
gas?
acid
Yeah.
turns into silver ions and
No, this is,
What is that?
hold on, I put the plus in the wrong place.
Oh,
I
okay.
see that.
That makes sense.
Still magic.
I didn't know if it was hydrogen gas or it was hydrogen.
No,
My bad.
it's an acidic environment.
That makes sense. Okay.
so if you expose silver to air and acid, it dissolves. Noted.
Wow.
Okay, so
That's
here's,
amazing
it's
to know.
exactly what Cohen said.
Oh, cool.
No,
They've been
So,
going less long than we
if-
thought.
if you take elemental silver, and this has to be a very, very, very specific reaction. So if you take silver and expose it to oxygen in an acidic environment, that's where the hydronium ions come from, then what's going to happen is that you're going to form silver ions. So what does that mean? What's the silver going to do?
Dissolve.
Yeah, the silver is going to dissolve. But this has to be, there's two conditions that have to be met. Number one, you have to have it in an acidic environment. So you'd have to take your silver and drop it into a container of acid. That by itself won't even do anything. But you also have to have a source of oxygen, which could be just the air, or you could like bubble up oxygen. You could generate oxygen and have that bubble up through the solution. Silver by itself isn't going to react. So if you just have elemental silver and you react that with oxygen in the air, do you get a reaction? No, which is why we use silver in jewelry. If silver would automatically react with oxygen, we would never use it. It's like, what happened? Oh, just reacted with oxygen. Okay. No, right? We use silver because it doesn't react, but you put it in an environment, it does. Okay. So I want to figure out the value of delta G. So let's start with the reduction equation. So start with this idea. What's getting reduced?
Oxygen.
The oxygen. How do you know?
Because it starts at 0 and then.
Because the elemental state of oxygen, any elemental substance has a value of 0. So my oxygen goes from 0 to, once you make water, it goes into
Minus
2 minus. So the oxygen got reduced. So you've got O2 turning into oxygen and water, right? And how many electrons are going to be involved?
4.
Why 4?
Because there's 2 oxygens and then.
Where am I going to put the electrons? On the reactant side or on the product side?
Reactants.
4 electrons over here. Cool. Are we balanced at this point?
No.
Oh, so horribly not balanced.
Balance in the middle.
So let's just start with the oxygens. I got 2 oxygens on the reactant side, so I got to put a 2 there. Now I've balanced out my oxygens. That's cool. Now I've got hydrogens. How can I balance those out? Oh. Now am I going to put hydrogen gas or hydronium ions? Hydronium ions. This is going to be important. Because if I just put hydrogen gas there, let's say that you think, oh, I'll just put hydrogen gas and two of those. If you put hydrogen gas there, would that balance the hydrogens?
Yes.
Yes. But what is it not going to balance?
Charge.
It won't balance the charge. Okay? But by putting the 4 hydronium ions, which makes it an acidic environment, now I've got 4 positive charges here. I've got 4 negative charges over there. The whole left side adds up to
0.
right side adds up to
0.
Now I balance on both of them. So that's why I said you have to balance both with number of particles and charge. That's why it's 4H plus. Now, the silver is simple, okay? So the silver is going to go from Ag into
Ag plus.
Ag plus. So I'm going to put 1 electron over here. So now what am I going to do?
Times 4.
Yeah. So I'm going to multiply everything by 4. So now I know my value of N is 4. Okay. So now we can tackle Gibbs free energy. So I've got my N value, which is 4. I got 96,500 joules per volt mole. But I need one other thing.
I need your E naught value.
I need my E naught value. Don't have the E naught value. So if you look at your chart, so now here's what you have to realize. Because I multiplied all of the silvers by 4, do I need to multiply my E naught value by 4?
No.
No, because this is not, your E naught value is not volts per mole. It's just volts. Even though I multiplied it by 4, I don't multiply my E naught value by 4. Okay? Don't do it. Am I going to change the sign of my E naught value from what it is on the chart? Gap Sean.
Yes.
Gap Sean? Is that a reduction or oxidation reaction?
That's not the. Oh, you're gonna reverse.
Oh, yeah!
I think with the total.
So we're going to switch that. We're going to switch. I was trying to decide if I was going to say swap or switch, so I ended up with something. Yeah, we're just going to swip it. Okay, so because we're going to swip it, what's the value of the silver oxidation? Negative 0.80. Now, on the oxygen, okay, and we're going to talk, especially when we get into galvanic cells where you have to like put electricity into it. We're going to spend a lot of time talking about water. So, can you find this reaction on your reduction potential?
Yes.
What's that value?
1.23.
1.23. So this is the value for the reduction potential of oxygen in an acidic environment. Okay? So I got 1.23, I've got a negative 0.8, you get that together, you get 0.43 volts. So, somebody take 4 times 96,500 times 0.43.
Negative 166,000.
What'd you get? What? Negative what?
166,000.
66,000. Now, there's a couple of ways you could do this. If you like writing out zeros, you can write this as zeros and you can leave it as negative 166,000. A lot of times when you get into we're eventually gonna be looking at charts of Gibbs free energy. Most of the time, you're gonna see Gibbs free energy actually expressed in kilojoules because of the fact that they're really big numbers. So if you do a simple division and divide by 1,000, because there's 1,000 joules in 1 kilojoule, then you get negative 166 kilojoules. Typically, Gibbs free energy is expressed in kilojoules because it tends to be pretty big numbers. If you want to leave it in joules, that's fine. If you're going to leave it in joules, I would suggest you write that in at least scientific notation. But here's what I beg of you. Tell me what this is. If you just write negative 166 times 10 to the 5th, whatever that number is, and you don't put units on it, I have no idea if you think that's in joules or that's in kilojoules. I do not care which one you do, okay? I can't begin to tell you how much I don't care. I would get used to working in kilojoules because that's what most of the time that's expressed in. But if you don't like that, it's like, man, that's a lot of effort to divide by 1,000. I just don't have it in me, okay? I realize the struggle is real. But I don't care what you do, just tell me which one it is, okay? Because if there's a big difference between negative 166 and negative 1.66 times 10 to the 5th, and no, I'm not going to guess. It's like, well, I guess I know what they meant. No, I'm not going to know what you meant. Okay. Let's do one more, and we'll call it good, because this one's a little bit more complicated. Not bad, though. No, actually, you got it. I'm just done.
Oh, yeah.
Oh, good.
All right, lock in.
Yeah, you have an assignment, but it's pretty short.
Lock in.
So you can lock in.
Lock in.
You can lock in. So stop the auto camera for a second.
Hold on. Hold on. Thank you.